Hey everyone, so this is actually a video we are making together on an advanced problem using Markov's and Chebyshev's inequality. And we noticed on Piazza that actually question 1 part E on discussion 7a was received a lot of attention, and we wanted to go over the problem so we can hopefully help some of you guys out.
So let's start. So the problem is you flip a biased coin until you get a heads. Let P be the chance of heads. We know that the probability of getting heads is at least 25%. So how many iterations of this game do you need to find a probability P to win? A probability P within 10% with a confidence of 90%. And we're working with the geometric distribution here because we're flipping until we get heads, right? So I guess initially, the way I wanted to solve the problem was similar to estimating the bias of the coin. So when we have that, right, we have a uniform distribution, right? But the problem with this, the problem here is that we don't know if our random variables are all going to have uniform probability, right? So none of this works. Even if you try and you try to solve it this way, the probability of p hat minus p is less than error, you'll notice that we have almost no variables. We don't know what p is, we don't know what p hat is, or the variance of p. So we can't use Chebyshev's on this yet, right? So we're gonna have to use another method.
Right, so as Sandy was saying, that this is a geometric distribution, and that's what we'd ideally want it to be. But right now we don't have any idea what the probability distribution looks like. So what we're going to try to do is approximate it somehow by setting another variable called u hat as an approximate expectation. And so as we see in the formulas up here, we know that u hat can be calculated by looking at each individual variable from I equal 1 through n, and summing up all the different xi's in order to get a mean expectation. And so because we want our approximated mean to be very, very close to the mean of a geometric distribution, we're going to set the expectation of u hat to equal the mean of a geometric distribution. And as you can see on the right here, we're going to go ahead and prove that the normal expectation of a geometric distribution is going to equal to 1 over p. So that means the expectation of mu hat should also equal to 1 over p. And so now that we've kind of made that constraint, now we can actually dig into the problem using Chebyshev's inequality. And so as you see with the following 3 equations here, we're going to use the definition of variance of an approximate expectation, which is sigma squared over n. And we're also going to try to make our approximation as close as possible by setting it greater than or equal to epsilon times mu, which is essentially saying we want the approximate mean that we find and the actual mean of the distribution. The difference between those two should be very, very small because it should be epsilon times the mean. And so now after solving or setting up these separate equations, we can see here that we're going to get to a situation where we have to figure out what the epsilon value will be. And so Sammy will proceed to explain that.
Right, so we know that the error has to be within 10%, right? But the problem is that because it has to be within 10%, so let's just calculate it, right? One step at a time. So p hat minus p is less than 0.1 p. Let's add p to both sides. So now we just have p hat is less than 1.1 p. And because Chebyshev's works on both sides of the bound, if we have an error, say this is p hat, right? We're going to have an error on the left hand side and the right hand side. But this error has to be symmetric because that's how Chebyshev's works, right? So we're going to have, we're going to take the reciprocal of everything. So flip the sign, get whenever p hat is less than or greater than or equal to 1 over 1.1 p. We do the same thing with 0.9 p. And so essentially what we have now is this little graph right here. We have 1 over 1.1 p is less than 1 over 1 p hat, which is less than 1 over 0.9. So essentially what we can do here is we can think of 2 error bounds, right? So let's focus on this left-hand side error bound. We have 1 over 1.1 p, right? Let's get everything into fractions because decimals are kind of nasty. So we have 10 over 11 p, right? And then we have 1 over 1 p. So let's get the same denominator, right? So let's multiply both sides by 11, and we get 11 over 11 p. So now we notice that the distance between 10 and 11p and 11 over 11p is just 1 over 11p, right? And because Chebyshev has to be symmetric, we know that the right-hand side of this also has to be 1 over 11p. So we get 12 over 11p. And if we look at this error bound, we do the same exact thing. So we have 1 over 0.9p, just times by 10 on both sides to work with fractions. We have 10 over 9p, 1 over p, and we want to get the same denominator again. So multiply both sides by 9, get 9 over 9p. Essentially, we have this. The distance between 8 over 9p and 9 over 9p is 1 over 9p, right? So we know that the right-hand side distance has to be symmetric as well. So we have 10 over 9p. And here's how we figure out which error to use. So essentially, we have the left-hand side error, right, which is 1 over 11p, which we calculated, and 1 over 9p. I'm just assuming like let p hat equal 1, right? Like that's like 100% of the time you get heads, right? Like the worst possible scenario. We know that our error has to be less than 0.1, right? So if we have 1 over 11, that's 0.09, so that works. But if we use this right-hand side error, then our error is actually 0.11, right? Which doesn't work. So we know that our error, our bound has to be 1 over 11. So that's how we get that.
Right, so as Sammy just explained, once we find the proper error bound, which is 1 over 11p, or 1 over 11, now we can finally use Chebyshev's inequality to figure out what probability we need, or how many iterations of this game we need to play in order to find a probability that's greater than or equal to 25%. So after we find 1 over 11, we want to go over here and use it to plug it into Chebyshev's inequality. So mu hat, we know this because this is going to be the x value that we're trying to find. And then 1 over p is the expected value of the geometric distribution. And then 1 over 11p is going to be the error bound we just found in the earlier step. And so we can set that less than or equal to, like in Chebyshev's inequality, to